Hello YouTube, so I hope you liked our last video on basics of linked list. If you haven't seen that video, we have the link for you in the description. So please check that out, but a little recap would help you guys find your way around linked list. So in previous video, we saw what is linked list, its benefits and its shortcomings, what are some of the common approaches to solve linked list problems in an interview, and in the end, we discussed some of the most common interview questions. Questions like reversing the linked list, merging two sorted linked lists, and how to find a cycle in a linked list. These questions, in our opinion, help you build a basic understanding on how to solve basic linked list questions and also help you develop the intuition to solve these questions. But before we proceed any further, make sure you hit that subscribe button and bell icon so that YouTube lets you know about our future videos in this series. We are hoping to launch a lot more of such interview related data structure and algorithm questions in near future. So press the subscribe button below. So in today's video, we are going to see some of the medium level interview questions and their solutions. First, we will explore two questions that are both use a common approach that we briefly saw in the last video using the auxiliary data structure. The first problem in this approach would be finding the next greater node in the linked list, and then we will look at the next one, which is the creating a copy of the linked list with random pointer. Then in the end, we will look at how to merge case sorted linked list. This is another variant of merging the two sorted linked lists that we looked in the previous video. So if you guys want a little refresher, please do so by finding the link in the description. So now please follow along with us. But if you're interested in a single question, you can follow the timestamp link in the comments for each of these questions in the video. So without much further ado, let's look at the first question of the day, which is returning the next greater node in the linked list. This is a mildly tough question where implementation is a little tricky than the actual algorithm. So let's look at the example first. So here we have our regular linked list which has the elements such as 4, 3, 6, 7 and null, which is the end of the linked list. So in return, we have to return an array or linked list where the elements such as it is the greatest than the current element in the list. For example, 6 will be the first place as it is closest to the 4 in the linked list from left to right. So it will be placed here in the output array. Then 3 is also similarly smaller than 6, so it will also be replaced by 6 in the resulting array. Then 7 will replace 6 in the resulting array because 7 is bigger than 6 and also closest to 6. And in the end, if something doesn't have a greater element than the one in the place, then we just replace it with 0. So if you guys want, you can pause the video for a bit and try to come up with the solution on your own. Alright, I hope you guys did your due diligence. Now, as I said that the solution is fairly simple, so this question is expecting us to use a stack so that we can stack all the elements in the data structure until we have a large element to pop all of them up. So for example, we first put 4 in the stack, then we will move on to 3, and then we will move 3 on top of the stack over 4, and also check at the same time that if 3 is greater than 4, which it is not, so in the end we will end up putting 3 on top of 4 in the stack. Then we move on to the next element in the linked list, which is 6, and then again we will compare all the top element of the stack to see if they are smaller than 6 or not. So here first we will pop out 3 because it is smaller than 6, and we will put that in the resulting array here. And then we'll also check with the 4 that if it is smaller than 6, and again it is smaller than 6, so we will put 6 again in the resulting array. Now we push 6 at the top of the stack as the next element to check for, and then we move on to 7. Again we do the similar exercise where 6 is smaller than 7 and we pop out 6 out of the stack and put 7 in the resulting array. Same goes with 7. Now we already hit the end of the list. There are no more elements left in the input list. So we will simply take rest of the elements that are in the stack, pop them one by one and place 0 at their indexes in the resulting array like this. Now that's all there to it for solving this question. Now let's quickly look at the code as well for the solution. So here we have defined the stack, which is based off the array of integers in the stack. This we have done to store the indices of each element and also the element value. So we will see in a bit how does that work. Now here we have the current as the head that we want to iterate over the linked list. So here we have started with the current head node and we will check till we hit the null. Now inside the loop we will check that if the top element is smaller than the current value element. If it is, then we will just keep on popping those elements one by one until we hit some element which is greater than the current element. And we will keep on placing them in the resulting array at the index that is associated with that element that we have stored in the first place. So here we are doing that. And when it comes that this current value is no more greater than any element left in the stack, then we will push it back in the stack like this. Here we are storing the index as well as the value of that element in the linked list node. Now we will just move on to the next node and repeat the same exercise again and again until we hit the end of the linked list. This small API we have created just to find the length of the entire linked list so that we can instantiate our resulting array in the first place. Now, as far as the time complexity and space complexity is concerned, so we have O2 times n space by initializing one stack but having two elements in it, one for index and one for the element itself, which is equivalent to On in the end. And we also ran the code in On time complexity since we only did one iteration over all the elements in the array. I hope that you guys have understood this problem. Main approach here is to use an auxiliary data structure like stack and help you to keep track of all the elements up till that point so that you can compare with the next greater element and store that value in the resulting list or array. Now let's move on to the next question that deals with a not so normal linked list. So in a traditional list, we only have value and the next pointer pointing to the next element. But in this problem, we are also given a random pointer that can literally point to any node in the list. So all we have to do is make a copy or deep copy of this exact linked list but with a new head and all the elements are copied again and again. Now as you guys can see that this is a little bit tricky since when we are going to copy the entire list, we won't know beforehand that where that node's random pointer will point to, because at that point we might not even have created that node for the new linked list. So please think for a moment that how you guys can do it. You can pause the video here. Don't think of coming up with the most optimized solution just yet, which is On time and On space, but just a brute force solution. So go on, we will wait for a bit. Alright, so I hope that you guys did your due diligence in coming up with the solution. So yes, a naive approach would be to create one-to-one entry of the original to the copy nodes as a key value entry in a hash table like this. So for example, you are pointing with X pointer here for 7. You will also make a copy for 7's copy in the hash table with the 7's copy pointer. So you make entry here like this, and you can do this for the rest of the nodes as well. Now all we have to do is do a second round of the traversal, look at the random pointer value in the original list and find its value from the hash table and link that accordingly in the copy list. Now definitely this gets us the solution in On time, but it also takes On extra space to store all those pointer locations for tracking purposes. Now of course there should be a better way than this, and there is actually, but it is a little tricky. So we will first develop the intuition to solve such problems. So remember that we can modify the next pointer in the original linked list. In reality, this is called tampering or mutating your input, but hey, no one said anything about not changing your input to bring down the complexity. Now what we need to do here is to insert the copy nodes in the original linked list as well. So as you can see here, this is what you will end up with in an original node, then immediately following its carbon copy. And don't worry about the random pointer just yet in the copy linked list node. They can be null for the moment. We will come back to take care of them in a little bit. So once we have our new list ready where each original node is followed by its copy node, now all we have to do is check the original node's next pointer value and then insert that as the random pointer for copy node. So here we will be replacing 3's next, which is copy of 3 random pointer, which is 7. Again, so 3 will be pointing to 7. So you can see the flow like this, that 3's next random pointer will be equal to 3's random's next pointer, which is 7's next pointer is the 7's copy. So now 3's copy will be pointing to 7's copy, and so on and so forth will happen to all the rest of the nodes. All we have to do is just move 2 nodes at a time. So when we were on 7, we will move to 3. When we were on 3, we will move to 13 after following these 2 nodes here, and then 13 to 10. So that way we won't be worrying about the actual copy of the nodes in the linked list. So in the end, all we have to do is just restore the original linked list and separate out the copy of the linked list into 2 heads, and then we will return the head of the copy linked list node. So also now let's quickly take a look at the code as well. So here we have the head of the linked list being passed as the input to the function. Now we start iterating over the nodes one by one here until we hit the end of the list. Now here we just have to create the new node like this with the node copy as a variable name, and also not care about the random pointer just yet. Just insert it in the linked list at the current place by doing this, and then we just move on one node after the another in the original linked list by doing the cur equals next. So in the second iteration, as we have suggested, that we are now replacing the copy node's random pointer with the actual list node random's next pointer, so that will be the copy node of that random pointer here like this, and we need to check is that it's not null, otherwise we will get a null pointer exception here. And as we have said in the actual example here, that we have to move 2 nodes at a time, one for the copy node and one for the actual node, so to iterate over the actual list instead of considering the copy nodes in the current list as well. So that we are doing like this by hopping over 2 nodes at a time. And in the third iteration, as we have said, that all we have to do is just separate out both the linked list, one for the original linked list that was given us as input and one with the copy linked list. So what we are doing here is just we are separating out the copy head from the actual node head by doing this, and in the end all we have to do is just return the dummy.next, which is tracking the copy head's head pointer. As far as the time complexities are concerned, so we did use O3n time complexity, one for this iteration, one for the second iteration, and one for the third iteration, but all in all it boils down to On time complexity. And we haven't used any extra space in this solution because we have just created all those copy nodes and then inserted them in the actual input list. So we were not using hash table in this solution. Now let's quickly look at the last question of the day, which is fairly complex as it is listed as the hard question on the lead code. So let's take a jab at it. So if you remember, this is a variant of the question that we solved in our last video where we merged 2 sorted linked lists. So here we are given 3 sorted linked lists. All we have to do is return this one sorted linked list which has all the elements from all the list in the sorted order. If you want, you can pause this video to try it yourself or just follow along to see how to solve this problem. So if you remember the algorithm to solve the previous variant of this question where we merged 2 sorted linked lists, doesn't it resemble to an already famous problem? Yes, I think some of you might have guessed it right. It sort of looks like merge sort, where we take bottom to top approach to first sort the elements in small chunks and then merge all the way up. Same is applicable here. We can club these n linked lists into pairs of 2, and after the first iteration we are left with k by 2 sorted lists. In the next iteration it will be k by 4. So as you can see that you can merge these lists in k log k runtime complexity, just like we used to do while we merge sort, which is equivalent to O(n) log n. And since a single merged linked list might take us O(n) time, so our overall complexity to merge k sorted list will be O(n) log k. But we have a different approach also, which also takes O(n) k log k time. Yes, we can totally use the unique property of fishing the minimum element from the top in a min heap tree for this particular problem. So here we create a min heap tree by using the head elements of all the linked list, just like this, 1, 2, and the one from the third list. And we know that min heap will take care of placing the minimum of all the head elements to the top by itself when we pop out the element from the top in O log k complexity. All we have to do is take the root element and place a new element from the same linked list until we hit the end of that linked list. So what we have done here is that once this one comes to the root, we have also inserted the one from this list because we already picked this from the root, and this goes here. And then next time when we pick out this one from the root, then this one will all obviously boil up to the root of the list. And what we have done at this point is that we will now put 9 in the linked list, and then it will also balance it up by having 2 being graduated to 1 in the next step. So as you can see that gradually one by one it will always give you the minimum of all the list in the min heap tree, and you will always pick out the minimum of all the elements in the tree by taking the root element. Now also let's take a quick look at the code, which is fairly simple once we have figured out the approach by doing this example run. So all we have to do is just check some basic edge conditions where like list should not be null and the length should not be equal to 0, otherwise just return that as null. Then we have to create this min heap tree. Here we are using the priority queue, so you can also use this, or you can also use the min heap tree your own implementation, depends on how you want to do it. And all we are doing is just like having a lambda function in there so that we can track that if a particular value is greater than or smaller than, to balance the tree accordingly. And now all we have done is that we are taking the root element from all these lists and we are checking that they are not null, and then putting at the head of the queue so that it can be balanced accordingly. Now we will just keep on doing until we have hit the end of the queue or the queue is empty. But we are doing is just taking the root of that priority queue element or that min heap tree, and all we are doing is putting the next element back in the queue at the tail of the min heap tree, and then we will just return the head of the value of the new linked list, which is sorted with all the elements from all the sorted linked lists. So let's quickly recap what we have seen in this video. So in this video we went over the first question, which is finding the next greater node in the linked list. Here we saw the approach of using auxiliary data structure in terms of stack and bringing the complexity from O(n) squared to O(n) and using just extra space, which is O(n) in this case. Next we have looked into the problem of copying the linked list with random pointer, where first we have seen that using a hash table gives us a solution of O(n) time complexity and O(n) space complexity, which we have further reduced by just mutating the original input list and getting the space complexity down to O(1). And in the end we looked at the merging of k sorted linked list, where we used min heap tree and also merge sort approach to merge all the elements from the k sorted linked list and finally get a sorted linked list that we return in the end. With this we would like to end this video. We learned quite a bit about linked list while making these videos, and we hope to bring more of such data structure and algorithms videos in future as well. So press that subscribe button and bell icon to get all our future updates. Also, if you like this video, you can press the like button as well. It helps to appreciate our cause, and YouTube shows these videos to interested folks like you. And if you are interested in the text version of these answers and other system design interview material, please head over to our blog, for which you can find the link in the description or here on your screen. Thanks for watching the video and keep practicing until the next time.